Welcome viewers to another lecture on analytical instrumentation. Today we will talk about Beer-Lambert Law. In today's discussion, we will cover the following topics: introduction, Beer-Lambert Law, Beer-Lambert Law, derivation of Beer-Lambert Law, prerequisites of Beer Law, limitations and deviations of Beer-Lambert Law. The Beer-Lambert Law, also known as Beer's Law, Lambert-Beer Law, or the Beer-Lambert-Boger Law. In 1729, Pierre Boger discovered the law. Lambert and Beer extended and corrected it further. The law relates the attenuation of light to the properties of the material through which light is traveling. The law is commonly applied to chemical analysis measurements and used in understanding attenuation in physical optics for photons, neutrons, and rarefied gases. The law is used in chemistry to measure the concentration of chemical solutions, to analyze oxidation, and to measure polymer degradations. The law also explains the attenuation of radiation through Earth's atmospheres. The Beer-Lambert law relates the attenuation of light to the properties of the material through which light is traveling. The law is applied to the analysis of a mixture of spectrophotometry without the need for extensive pre-processing of the sample. Beer law states that the absorption of light is directly proportional to both the concentration of the absorbing medium and the thickness of the medium in the light path. That is, A equals epsilon Lc, where epsilon is the molar absorptivity. Lambert law states that each layer of equal thickness of an absorbing medium absorbs an equal fraction of the radiant energy that traverses it. Hence, transmittance T equals I by I naught, where I is the radiant energy transmitted, I naught is the incident radiant energy. Percentage transmittance equals 100T. Absorbance A equals log 10 base I0 by I, or A equals log 10 base 1 by T equals log 10 base 100 by percentage transmittance. A combination of the two laws, that is Beer law and Lambert law, defines the relationship between absorbance A and transmittance T. It states that the concentration of a substance in solutions is directly proportional to the absorbance A of the solution. That is, A equals epsilon Bc, where epsilon is the molar absorptivity with the units of liter per mole per centimeter, B is the path length of the sample, and C is the concentration of the compound in solution moles per liter. The Beer-Lambert law can be divided from an approximation for the absorption coefficient for a molecule by approximating the molecule by an opaque disk whose cross-sectional area sigma represents the effective area seen by a photon of frequency omega. If the frequency of the light is far from resonance, the area is approximately 0, and if omega is close to resonance, the area is a maximum. Taking an infinitesimal slab dz of sample, Beer-Lambert law is derived. Consider a beam of parallel monochromatic light with intensity I0 striking the sample at the surface as shown in the figure below, such that it is perpendicular to the surface. After passing through the path length dz of the sample, which contains n molecules per cubic centimeter, the intensity of the light reduces to IT. Now consider a cross-section of the block having an area S and an infinitesimal thickness dz placed at a distance z from the surface. If the sample has n molecules per cubic centimeter, the number of molecules present in the infinitesimal block would be Ns dz. If each molecule has a cross-sectional area sigma where photons of light gets absorbed, then the fraction of the total area where light gets absorbed due to each molecule would be sigma by S. The total fractional area for all molecules in the block where light gets absorbed would therefore be number of molecules into fractional area for each molecule. That renders Ns dz into sigma by S equals sigma n dz. If Iz is the light entering the infinitesimal block considered and the light absorbed due to the absorbing particles is di, then the light exiting the slab would be Iz minus di. The fraction of light absorbed would therefore be di by Iz. Now, since the fractional area is the probability of light striking a molecule, the fraction of light absorbed in the block is equal to the fractional area occupied by all the molecules in the slab. That is, di by Iz equals minus sigma n dz. Note, the negative sign is placed to indicate absorption of light. We integrate this infinitesimal block for the whole sample from z equals 0 to z equals b, where b is the path length of the entire solution. We get log natural it minus log natural I0 equals minus sigma nb. Thus, log natural it by I0 equals sigma nb. One can correlate the number of molecules per cubic centimeter of sample to the concentration of the sample in moles per liter using the relationship C equals n into 1000 by 6.023 into 10 raised to 23. Therefore, n equals 6.023 into 10 raised to 23 into C by 1000 equals 6.023 into 10 to the power 20 into C, where C is the concentration in moles per liter, N is the number of moles per cubic centimeter, and 6.023 into 10 raised to 23 is the Avogadro's number. N into 1000 would be therefore molecules per liter, as 1 liter is equal to 1000 cubic centimeter. Substituting this term for n in the above equation, we get minus log natural it by I0 equals sigma into 6.023 into 10 to the power 20 into C into B. To simplify this equation further, we convert to log using the term 2.303 into log x equals log natural x. Thus, we get minus log it by I0 equal to sigma into 6.023 into 10 raised to 20 into C into B whole by 2.303. Hence, log I0 by it equals sigma into 6.023 into 10 raised to 20 by 2.303 into Cv. The term log I0 by it is nothing but absorbance A, while the term in the bracket is a constant and can be replaced by the coefficient epsilon. Thus, epsilon becomes sigma into 6.023 into 10 raised to 20 by 2.303. Thus, we get A equals epsilon Cb. Since we have used moles per liter as the units of concentration, epsilon stands for molar absorptivity. If the units of concentration were gram per liter, then epsilon would be replaced by small a, absorptivity. By definition, the molar absorptivity epsilon at a specified wavelength of a substance in solution is the absorbance at that wavelength of 1 mole per liter solution of the substance in a cell having a path length of 1 centimeter. The unit of molar absorptivity is liters per mole per centimeter. There are 6 conditions that need to be fulfilled for Beer's law to be valid. These are: the absorbers must act independently to each other, the absorbing medium must be homogeneous in the interaction volume, the absorbing medium must not scatter the radiation, that is no turbidity, the incident radiation would preferably be monochromatic and have at least a width that is narrower than that of the absorbing transition. The incident radiation must consist of parallel rays, each traversing the same length in the absorbing medium. The incident flux must not influence the atoms or molecules. It should only act as a non-invasive probe of the species under study. In particular, This implies that the light should not cause optical saturation or optical pumping, since such effects will deplete the lower level and possibly give rise to stimulated emission. If any of these conditions is not fulfilled, there will be deviations from the Beer law. The linearity of the Beer-Lambert law is limited by chemical and instrumental factors. There are certain causes for nonlinearity of Beer-Lambert law. Those are deviations in absorptivity coefficient at high concentrations more than 0.01 mole due to electrostatic interactions between molecules in close proximity, scattering of light due to particulates in the sample, fluorescence or phosphorescence of the sample, changes in refractive index at high analyte concentration, shifts in chemical equilibrium as a function of concentration, non-monochromatic radiation. Deviations can be minimized by using a relatively flat path of the absorption spectrum, such as the maximum of the absorption band, and no stray light. For additional reading, the viewers can refer to the following references.